Now today we are moving towards the second unit, that is design of slab. So here in this unit we are going to deal with four types of slabs. Already in the first introductory lecture, I have told you in detail about each and every unit. Brief introduction I have already given. Some details also I have given to you. Okay. So here in the design of slab, basically one-way slab is there, two-way slab is there, one-way continuous slab is there, and cantilever slab is there. This is very easy chapter. Okay, this is very easy. Just some four types of slabs are there, and their stepwise design procedure is there. Just you have to follow the procedure, and you have to check the you have to take the checks whether whatever design you have given it is sufficient or not. That's it. That that is the only thing we need to do here. As all of you already know that what is the meaning of slab, where it is provided. So I'm not going into the details of that. So here we will start now. So basically there are two types of basic slab, that is one-way slab and two-way slab. Now here on the screen your two diagrams are there. Okay, the first is of one-way slab. This first diagram is of one-way slab, and the second diagram, this diagram is of two-way slab. Okay, now what is the meaning of one-way and two-way? We will see that, but before that, here you see this length. If you consider this rectangle as a slab, then this horizontal length in x direction it is called as Lx. This is vertical length in y direction. This is called as Ly. Okay. So and here the numbering is given 1, 2. Here it is 3, then 4. It is nothing but it is beam number. So 1 to 2 is one beam. 2 to 3 is another beam. Similarly, 3 to 4 is also one beam, and 1 to 4 is also beam. So this slab is supported on beams. Okay, at the end of the slab, there should be beam. We always know that slab is there. After slab, beam is the next structural element. After beam, column must be there, and after column, footing is there. Okay. So now, when we call the slab as a one-way slab and when we call the slab as a two-way slab, that is the question. So when your Ly by Lx ratio, that is the length in y direction to the length in x direction, or you can say span in y direction to the span in x direction. When your Ly by Lx ratio is greater than 2, the ratio of these two quantities Ly by Lx, here it is written over here, Ly by Lx is greater than 2, then your slab is one-way slab. Okay, when your Ly by Lx is greater than 2, then the slab is called as one-way slab. And when the ratio of Ly by Lx is less than or equal to 2, then it is called as two-way slab. Then it is called as two-way slab. Now what is two-way and what is one-way slab? See here. Now this is the one-way slab. Okay, and these two diagrams given over here are the diagrams which shows the deflection. Okay, this shows the deflection. Now, as you see from the diagram, this is our shorter span. So this is shorter span means the length of this Lx is less as compared to Ly. So this is our shorter span, Lx. Ly is our longer span. Ly means length in y direction. Lx means length in x direction. So x length is smaller than this y length. That is why Lx, we call this Lx as a shorter span and this Ly as a longer span. Now this type of loading is acting on the slab. This is the load distribution which is acting along the beam. Okay, when you construct the slab, over the slab, suppose one more floor is there, then or there will be floor finishes there on the slab. Okay, tiles weight is there, and then live load is also there. And if it is terrace slab, then on the slab POBA will be there. Okay, some people afford to put tiles also. So that weight is distributed from slab to the beams. Now here I already told you this 1, 2, 3 and 4 are the beams. So the weight which are coming on the slab is distributed along these beams in such a fashion. Here the structure is showing over here. On the longer beams it is distributed along a trapezoidal area, and for the beams along the shorter span it is distributed along triangular area. Okay, so this is the distribution. Then if you see the deflection along the longer direction, then this deflection is increasing up to some point, and then it is throughout remain constant. Okay, this is throughout remain constant. From, if you see from this bottom, it is increasing up to certain limit, and then it will remain constant. From right hand side also, from right also it is increasing. From top also it is increasing, and after this point it is remain constant. Okay, so this is the deflection in longer span. Okay, in the case of one way, in the case of this slab, and if you see this shorter span, the deflection curve is parabolic. Okay, if you start from left hand, the value is increasing, 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 and it is maximum at the center also. And if you see from the right side, the value is again increasing, 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 and it is maximum at the center again. Okay, so whenever this type of deflections are there, on longer direction, the deflection for most of the time is constant, and along the shorter direction, the deflection is increasing and it is of parabolic shape. We are always going to provide the steel in the slab parallel to the x direction or along the shorter span or parallel to the shorter direction. Okay, because here the deflection is constant, but here the deflection is not constant. Each and every point it is varying. So we are providing our main steel in this direction. Okay, that is parallel to x direction. And another steel which is called as distribution steel, that distribution steel will be provided along the y direction, that is parallel to y direction. So a slab in which main steel is provided in shorter direction and along longer direction the distribution steel is provided, such a type of slab is nothing but a one-way slab. Okay, such a type of slab is nothing but one-way slab. Similarly, if you go for the two-way slab, so now what is the difference? As you see from this deflection diagram, again the parameters are same. This is your shorter span Lx, this is your longer span Ly. Okay, the beams are same, 1, 2, 2, 3, 3, 4, 1, 4. But what is the difference? Here if you see along the longer direction, the deflection is parabolic, and along the shorter direction also it is parabolic. Okay, so this type of case is nothing but it arises in the two-way slab. In one-way slab, what happens? Along the longer direction, the deflection is constant, and along the shorter direction, it is varying in parabolic manner. But in two-way slab, the deflection at a longer span as well as at shorter span, both deflections are the parabolic. So in this case, the deflection is not constant at each and every point. As you are moving forward, your deflection is going to change. So that is why in this type of slab, the main steel is provided along both the directions. The main steel is provided parallel to x direction as well as the main steel is provided parallel to y direction. So here in the two directions, the main steel is provided. So it is called as two-way slab. Okay, and here in the case of one-way slab, along the shorter direction, only in one direction main steel is provided. So this is called as one-way slab. Why it is provided in one direction? Because of this deflection problem. Okay, so this is the introduction about one-way slab and two-way slab. Generally, I am going to tell you one thing. The percentage of steel in the slab varies between 0.2% to 0.4%. Okay, what is the percentage of steel in the slab? It is 0.2% to 0.4%. That much steel is sufficient in the slab. Okay, for to calculate the percentage of steel, your formula is 100 AST upon BD. Okay, the formula is 100 AST upon BD. 100 is constant. AST means area of steel, whatever area you have provided, divided by BD means B is the width of the section and D is the effective depth. Okay, D is nothing but effective depth. From this you will get the percentage of steel. So initially while designing the slab, we always assume the percentage of steel. We generally assume the slab may require 0.3% of steel, and we will start our design. And at the end, we will check that whether our design assumption is right or our assumption is wrong, or accordingly we have to modify some steel bars. So this is the introduction about one-way slab and two-way slab. So the key point here, you remember this. Why the steel is provided only in one direction? Because the only in X direction the parabolic deflection is there. In Y direction deflection is constant. So distribution steel is there in Y direction. In the case of one-way slab, the basic criteria to identify one-way slab is Ly by Lx ratio must be greater than 2. That is, this longer span to the shorter span ratio must be greater than 2. In the case of two-way slab, if you see deflection profile in Y direction, the deflection is parabolic. In X direction, the deflection is also parabolic. So here the deflection changes at every point in X as well as in Y direction. That is why in this case, the main steel is provided in both the direction, X direction as well as in Y direction. Okay, so now we will move to the next part, and the criteria for this is most important for two-way slab, Ly by Lx ratio must be less than or equal to 2. Okay, for two-way slab it must be less than or equal to 2. For one-way slab it must be greater than 2. So now, next slide here now. Okay, so we will demonstrate through the problem how to design the one-way slab. Okay, so now I will dictate the problem first. You write down the problem and simultaneously take your calculator, IS code and notebook. You have to write, you have to do the calculation and simultaneously check the page numbers on which the clauses are given. I will tell you that. Okay? Yes, no? Are you listening me? Hello? Okay. So sometimes your audio is also not clear. So if you mention in chat yes sir, no sir, so that I can understand. Okay. So now here, take down the problem first. Design a simply supported slab design a simply supported slab supports on supports on a masonry wall supports on masonry wall having dimensions 3 meter by 6.5 meter 3 meter by 6.5 meter. The slab carries a live load of the slab carries a live load of 4,000 Newton per meter square. 4,000 Newton per meter square. Use M20 and Fe415. Use M20 and Fe415. Okay. Now here if you read the problem carefully, what they have given, design a simply supported slab. Okay. Supports on a masonry wall. So it is supported on the wall. Okay. and having dimensions 3 meter by 6.5 meter. So your shorter length is 3 meter length in x direction. You always take almost take a length in x direction is a shorter length. It is not a rule and it is also not necessary, but for our convenience we will take in that way. So your shorter span is 3 meter, shorter length is 3 meter, longer length is 6.5 meter. It is already given. Then the live load on the slab is given. What is the live load? 4000 Newton per meter square. So if you convert it, then it will be 4 kilonewton per meter square. Use M20. So M20 is nothing but FCK. 20 Newton per mm square. Strength of concrete is given to you. Similarly, strength of steel is also given to you. Fe 415. 415 is nothing but yield strength of steel. So the value of Fy is also given to you. It is 415. So now here, just a minute. Okay. So Ly by Lx ratio is 6.5 by 3, 2.16. Ly by Lx ratio is greater than 2. So it is one way slab. Then this why we are taken like in this way, because in IS 456 2000 annexure D D 1.11 page number 90, this condition is given. Have you got this? Have you read this? Yes, no? My voice is visible, audible, sorry. Screen is visible and voice is audible. Nobody is replying. Okay. So I have got one message. Yes. Okay, good. So this condition is given in the IS code. If you open your IS 456 2000, if you go on page number 90, you will get this condition. And in the examination, this IS code is allowed to you. Okay, you have been permitted to allow IS code in the examination also. So there is no need to remember or by heart this formula. Okay, just you remember the page number where this formula is given. Now the next thing, for slabs, we are assume percentage of steel 0.3% to 0.4%. Okay, normally. So I have already told you 0.2% to 0.4% it is generally taken for the slab. So the notation for percentage of steel, it is PT. So here I am assuming that assume 0.3% of steel. Okay, here I have assumed 0.3% of steel. So again you need to go to the IS code. So this is our percentage of steel assumed, 0.3% of steel. So why we are going to assume the percentage of steel? Because we want to calculate the depth of the slab. Our step number 1 is whether to decide the slab is one-way slab or two-way slab. That step is over. Now we come to the conclusion that the given slab is one-way slab. Now our next job is to calculate the depth of the slab. What should be the depth of the slab, that we need to calculate. So for that, what we have done, we have assumed 0.3% of steel. This is the assumed value. Okay. So for now, we need to go to page number 38 of IS 456 2000. Okay, there is one graph is given to you, which on y-axis modification factor is given, and on the x-axis percentage of steel required and provided, that is given. Have you seen that graph, or shall I stop my screen share and open the IS code? Just wait, I will open the IS code over here. So this is the IS code. Now we will move to page number, I think it is given as 36 now. So page number 36, 38. So we will read some clauses from here so that you will understand what is going on. Okay, so here, see this graph. Here what is given, on y-axis modification factor is given, and on the x-axis the percentage tension reinforcement is given. Okay, so the formula for that is Fs is equal to 0.58 into Fy, area of cross section of steel required divided by area of cross section of steel provided. So here this Fs is nothing but this Fs is the value of this graph. Here you see 5 lines are given, 1, 2, 3, 4, 5. So Fs 290, Fs 240, Fs 190, Fs 145 and Fs 120. From this we are going to calculate the modification factor. And why this modification factor is required? To calculate the depth to calculate the depth of the slab, modification factor is required. Why? Because if you go to page number 37, here you can see that to calculate the depth, span to depth ratios are given. Okay, here if you see basic value of span to effective depth ratio, span to effective depth ratio for span up to 10 meter. So 10 मीटरच्या आतपर्यंत जे जे स्लॅब आहेत त्या स्लॅबचा स्पॅन टू इफेक्टिव्ह डेप्थ रेशो तुम्हाला दिलेला आहे. तर तो स्पॅन टू इफेक्टिव्ह डेप्थ रेशो काय आहे? इफ द कॅन्टिलिव्हर स्लॅब इज देअर देन इट इज 7, if the simply supported slab is there then it is 20, and if the continuous slab is there then it is 26. So in our case our span to depth ratio is 20. Our slab is just simply supported by the walls. Okay, nothing there is no condition given to us in the problem. So our slab is simply supported slab. So our value is the span to depth ratio is 20. Okay, so the span to depth ratio is 20, but they have given again, now if you read this, see what they have given. Depending on the area and the stress of tension reinforcement, the values in A means this is A, this whatever we are using, this is the A. The values given in A or B shall be modified by multiplying with the modification factor. Now here you will get that term modification factor. तो कुठं मिळेल म्हणून ते पण सांगितलंय त्यांनी पुढं. The modification factor obtained as per figure number 4. म्हणजे थोडक्यात त्यांनी काय सांगितलंय की जर तुम्हाला स्लॅबची डेप्थ काढायची असेल तर स्पॅन टू इफेक्टिव्ह डेप्थ रेशिओ जो आहे हा स्पॅन टू इफेक्टिव्ह डेप्थ रेशिओ हा तुमचा स्पॅन टू इफेक्टिव्ह डेप्थ रेशिओ फॉर सिम्पली सपोर्टेड साठी किती आहे? 20 आहे. ओके, पण तुम्ही त्याच्यामध्ये मॉडिफिकेशन फॅक्टर कन्सिडर करायला पाहिजे. यू शुड कन्सिडर मॉडिफिकेशन फॅक्टर. And from where you obtain this modification factor? So you will obtain from figure number 4. And what is figure number 4? This is your figure number 4. See here. So this is your figure number 4. Now are you getting some link? Why we are seeing this graph and why we are doing all these things? Okay. So here what we do always, we first calculate which line. We must have to see which line we should see. आपल्याला नेमका आता याच्यातली कुठली लाईन बघायची हे आधी ठरवावं लागेल. So for that the formula is given. Fs is equal to 0.58 Fy, area of cross section of steel required divided by area of cross section of steel provided. So now here we will assume that whatever area of cross section of steel is required, that area we are going to provide. As simple as that, because we are designing the slab. जेवढी काही त्या स्लॅबची स्टीलची रिक्वायरमेंट असणार आहे तेवढा आपल्याला स्टील त्याला द्यावंच लागणार आहे. We need to provide that steel. So that is why we will take this ratio as 1. Whatever the area of steel is required, that we are going to provide. Suppose now, if 100 mm square steel is required, then we are going to provide 100 mm square steel. So 100 divided by 100, what will be the ratio? The ratio is 1. Okay. So here, if this ratio becomes 1, then what remains? 0.58 into Fy. Now the calculator is with you. You do the calculation. Fy means what? Yield strength of steel. The yield strength of steel is already given to you in the problem. They says that Fe415. So 415 is nothing but Fy. So if you multiply this 0.58, if you multiply this 0.58 by 415, you will get the value of Fs. Okay, and from that you need to select the line. Suppose now, if I got the value 187.5, suppose something that sort I got the value. So here there is no value of 187.5. So you should see the nearest value. So 187 च्या जवळ काय आहे 190. मग मी ही 190. Now for that we will go to the IS code now. So I will open the IS code. So page number 73. Page number 73. Here you need to use this table. See the heading of this table. Table number 19, design shear strength of concrete. Okay. So to calculate the design shear strength of concrete. Design shear strength of concrete means what? The permissible shear strength we want to calculate. That is tau c. So here this left hand shows you the 100 AST upon bit, that is the percentage of steels are given over here. Here the concrete grades are given, different grades of concrete, M15, M20, M25. So our concrete grade is M20. So we need to look up in between these values, so which are given in this table. Now what is our percentage of steel? Now our percentage of steel is 0.2%. Okay, our percentage of steel is 0.2%. So we know that for 0.15%, the value is 0.28 given in the table, and 0.25% the value is 0.36. Now if you do the interpolation, then you can get the value for 0.2%. Okay, so the value which is given here for the 0.2%, that value here, that value works out to be 0.32. That is 0.32 Newton per mm square. I hope you understand. The simple interpolation is there. I have also written the formula here also. What are the values for the better understanding here. From that table, for 0.15 percentage of steel, we got the shear stress, that is tau c value 0.28. 0.25 percentage, we got that value 0.36. Okay. So after doing interpolation, we get this value 0.32. So here I have written 0.32. Now permissible shear stress, that is tau c is equal to K into this tau c dash. So K into tau c dash is 1.3 into 0.32. So from where this 1.3 comes? So again from clause number 40.2.1.1, page number 72. From there that this value of K is come, this coefficient 1.3, and if you multiply by this coefficient to this value 0.32 tau c dash, you will get the permissible stress. Permissible stress means allowable stress. Remember this. Permissible stress means allowable stress. So here you can see that the stress generated in the slab, that is nominal shear stress, it is 0.17. Generated 0.17, and permissible or allowed value is 0.42. So here your tau v is less than tau c, hence your slab is safe in shear. Otherwise, if your permissible value is 0.42 and here you are getting your nominal shear stress tau v value is something about suppose 0.60, which is greater than 0.42, then your slab will not be stable in shear. It may fail in shear. So at that time you have to either increase the depth of the slab to resist that shear, or either you have gone for the shear reinforcement. So therefore, here you see that if the value of the shear stress, that is nominal stress, is less than the permissible stress and allowable stress, then your slab is safe in shear. Now we will see this table from where this 1.3 comes. So we will go to IS code once again. So here is the IS code. The table, here is the table. The design shear strength of concrete. See, this is 40.2.1.1. For solid slab for design shear strength for the concrete shall be Kc K into tau C, where K has the values given below. So overall depth of slab in mm and the value of K. So overall depth of the slab. So now here if you look this last column, then here they have mentioned that 150 or less. So 150 or less overall depth. So what is the overall depth? They have said here overall depth, not effective depth. Remember this. So what is the overall depth of our slab? So I think it is 135 or something. No, overall depth we have provided. So it is less than 150. Okay, so less than 150. So what is the value? 1.3. So we have used that 1.3 is as a value of K here. So after using that now, here K 1.3, 1.3 into 0.32, it is 0.40. So after this, the check for shear is over. Once you get this value of tau B is less than tau C, that is allowable, then your slab is safe in shear. Then your slab is safe in shear. After that, check for deflection. So check for deflection, we need to take that check. So to take the check for deflection now, see, consider the percentage of steel which we have provided. So what is the percentage of steel which we have provided? The percentage of steel is 0.4%, as we already know that 0.4% we have provided. So now go to this FS, that is figure number 4, page number 38. Okay, go to the figure number 4, page number 38, which we have already seen while evaluating the depth. So Satyavan More, please switch off your video. So here, if you go to figure number 4 and page number 38, for that, first of all, you need to calculate the FS. What is the FS? So the value of FS is the formula you already know. FS is equal to 0.58 Fy into AST required divided by AST provided. This formula is also given in the IS code below this figure. So now we are going to put our values. Initially what we have assumed that whatever may be the required, that we are going to provide. So we have taken this ratio as a 1. But now what is the case? The AST required is 395.27, which we have already calculated. And we are providing the AST is 471.23, which that we have provided. So if we put the values, then we get Fs is equal to 0.58 into Fy is 415, and these two values if we put over there, we will get Fs is equal to 201.9. So we round up this value of Fs to the nearest value. So nearest value is 190. Okay, so the nearest value here, we got this value as a 190. So now see the line of 190 for the percentage of steel 0.4%. 0.4%. So from that we will get the value of modification factor. Okay. To calculate the required depth for deflection, we are doing all these things because now we are going to check the deflection. So now, as you already know, in figure number 4, multiple graphs are there. I hope you are now with the IS code. See that on y-axis the modification factor is given. On x-axis, you will get the percentage of steel, and you have now finalized the graph which line you are going to see, that is 190 Newton per mm square. So if you project all these values onto this line, that is, if you project this 0.4% on the line of 190 Newton per mm square, you will get modification factor as 1.65. So near about value 1.6. Instead of 1.65, if you take 1.6, then also it is okay. If you take 1.7, then also it is okay. Okay, so you have to take that value by judgment where it will come. So 1.65, that is the modification factor. So now D required for deflection. So depth required for deflection, again same formula, span divided by 20 into modification factor. Okay, by using this formula only, we have calculated the depth also. Now by using the same formula, we are going to calculate the depth required for deflection. D required for deflection is equal to span divided by 20 into modification factor. Just put the values, you will get this answer. So the depth required from the deflection criteria is 95 mm. Okay, so minimum that much depth you should provide. Otherwise, if you provide the depth from the bending moment criteria, if you remember that when we have taken the check for depth, okay, our bending moment depth required for sustain that bending moment is, I think, 75 mm, somewhat 75. Okay, so if we go back here, you can see the depth required. Check for depth here. When we took this check for depth, what depth we got here? So 75 mm. This is the depth from which the bending moment criteria. So this was our bending. Okay, 75 mm depth was there. Now, if you provide 80 mm or 85 mm, whatever I had told you in the last lecture, then it will fail, because for deflection, what depth is required to resist the deflection? To resist the deflection, the required depth is 95 mm. The required depth is 95, so minimum you should provide 95. So here, but our provided depth is, what depth we have provided? 135 mm. So we have provided 135 mm, which is greater than the required depth for deflection. Hence, it is safe in deflection. Hence, it is safe in deflection. As the check of deflection is depending upon the percentage of steel, I have given you two direct things. When to you take the check for deflection, and when it is okay if you don't take the check for deflection. You go through this here. So if percentage of steel provided is greater than the percentage of steel assumed, then calculate the depth and check it. Okay. And if the percentage of steel provided is less than the percentage of steel assumed, then no need to check the depth. Okay. Now let us see what has happened in our case. So here, if you see, the percentage of steel provided is 0.4%. Okay, so here our PT provided is 0.4%, and percentage of steel assumed. What we have assumed initially? We have assumed initially the percentage of steel is 0.3%. If you remember, we assumed 0.3%, and at the end we have provided 0.4%. So our PT provide is greater than PT assumed. So that is why you have to calculate the depth and check it for the deflection. So that is why we have done this calculation. We have calculated the depth and we have taken the check for deflection, whether this depth is sufficient or not. Okay, if the reverse case is there, now if you provide assumed percentage of steel, assumed value is greater. Now if you assume maybe 0.4%, and if you provide 0.3%, then you will come under this second case. Okay, there is no need to check the depth, because that depth will be always what we can say satisfies the criteria. So in this type of case, you may directly write that as the percentage of steel provided is less than the percentage of steel assumed, so the deflection criteria is satisfied. You can directly write down this sentence. Okay, so in our case, the case is that we provide 0.4%. Initially, we assume 0.3%. So our percentage of steel provided is greater than the percentage of steel assumed. That is why we have taken the check for that. Now, after this, now we need to take the check for development. So next is the check for development. So the development length, you might be knowing that. Now suppose the junction is there. Suppose the beam and column are meeting at a point. That point we called as always called as the junction. So if you observed on site or if you observed carefully, then the bars which are coming to the beam are inserted in the column to the some extent. Okay, as the bars which are coming from the beam are not tied up there itself in the beam. Those bars are extended in the column up to the some length, and that length is called as the development. Okay. So for the development length, there is one formula to calculate the development length, and this formula is given over here. This is the formula to calculate the development length. LD is equal to pi sigma s upon 4 tau BD. This formula is also given in the IS code, that is clause number 26.2.1, page number 42. So we will go to the IS code and we will see this formula, and afterwards we will put the values over here to calculate the development length. So here we will go to the IS code. What was the page number? Anybody noticed what was the page number? Nobody knows. So clause number 26 point something was there. So we will move to the clause number 26. So where here it must be there. What is our clause number 26? See, here the formula is given. Okay. Now the formula is given over here in the IS code. This is the formula for development length. LD is equal to pi sigma s upon 4 tau BD. Clause number 26.2.1 of development length of bars. So where pi is equal to nominal diameter of the bar. Now the each, what we can say, they have specified each term, what each term indicates. So the, if you see here, the phi indicates the nominal diameter of the bar. The nominal diameter of the bar. Then sigma s is nothing but this term sigma s is equal to stress in bar at the section. Okay, so this is called as stress. So sigma s, the value of sigma s is generally taken as 0.87 into Fy. 0.87 into Fy. And now this tau BD. Tau BD is nothing but design bond stress given in 26.2.1.1. So for this tau BD value, we need to look up the table number 26.2.1.1. So we will move to that table 26.2.1.1. So we will see that here now. Just below that, that table is there. 26.2.1.1 design bond stress in limit state. Okay. So here the grade of concrete is given and different values of tau BD is given. Here is the value of tau BD in Newton per mm. So our grade of concrete is now M20 is the grade of concrete. And what is the value for M20? It is 1.2. This is the value for M20. For M25 it is 1.4. For M30 it is 1.5. For M35 it is 1.7. And for M40 it is 1.9. Again, you don't need to add any value. Everything is given in IS code. Just you should know that what is given on which page number and what clause number you need to use. Okay. So here again they have further told us that for deformed bars confining IS 1786, these values shall be increased by 60%. Okay. For the bars in tension, normally we increase the value by 60% for the bars in tension. So here they said that increase this value by 60%. Now if you want to increase the value by 60%, you need to multiply the existing value by 1.6. Okay, and for the bars in compression, here for the bars in compression, the value of bond stress bars in tension shall be increased by 25% further. Okay, so what we need to do, if the bars are in tension, then we have to multiply this value of tau BD, whatever given over here in this table. So here the values of tau BDs are given 1.2, 1.4, all these values are given. Okay, but uh, these values needs to be multiplied by 1.6 if the bars are in tension, and if the bars are in compression. So in the case of column, the bars are always in the compression. So the bars are in compression, then you need to multiply this value of whatever you have obtained by multiplying 1.6. Again, you have to increase that value by 25%. So again, you need to multiply it by 1.25. Now, for example, if I tell you for the bars in compression now for M20 concrete, if the value of bond stress is 1.2, then first of all you need to increase this 1.2 by 60%. So that is multiply this 1.2 by 1.6, and after that again multiply that value by 1.25. So you will get the design bond stress in concrete. So similarly now we will see this in our PowerPoint presentation. The value here. Now LD is equal to, the formula is already given. LD, we know the formula. So now just put the values. Here LD is equal to 5. Pi is the bar diameter. So we have assumed initially the 10 mm bar. This is our bar diameter. Okay. So 10 mm is the bar diameter into sigma s. I have already told you this is the value of sigma s. So sigma s is nothing but it is 0.87 into Fy. So 0.87 into Fy is 415. Whatever the value you will put over here. So divided by 4 tau BD. So 4 is constant, which is as it is. Tau BD. Tau BD, the value of tau BD is 1.2 for M20 grade of concrete. We have already seen in the table. Okay, table on page number 43, clause number 26.2.1.1. I have written here the clause. Okay, so we have already seen that value is 1.2. So again now this steel is at the center, so tension will be there. So the steel is subjected to tension now. So for tension and toss steel, we have to increase it by 60%. Deformed steel bars confining to IS 1786. So we have multiplied that the given quantity by 1.6. So if you put all the values and you will calculate, then you will get the value of LD, that is development length, as a 470.11 mm. Okay, this is your development length. Now you go to the clause number. Now if you move further to the clause number 26.2.3.3, page number 44. Okay, so there one formula is given. That formula is 1.3 m1 upon vu plus L0. This formula is also in the regard of development. So finally, if whatever may be the value of this LD, development length, that value should be less than this value, which I have indicated over by pink bracket. So if the value of LD is less than this 1.3 m1 upon vu plus L0, then the criteria for development length is satisfied. Okay. Then bond stress will not exceed and your structure will be safe. But if the value of this 1.3 m1 upon vu plus L0 is greater than this LD, then you need to revise the section. Okay. Then you need to revise the section, means you have to, what we can say, change your depth, and once again you have to do all the calculation and take all the checks. Same. So now this formula is also given on page number 44, clause number 26.3.2.2. So that formula we want to see here somewhere. Where is the IS code? So that formula may be somewhere here. This is the formula. The formula is given. This is the formula. M1 upon V plus M0. So we have taken here 1.3. 1.3 M1 upon VU plus L0. So where VU is the shear force. We are not using the notation for shear force is VU. And now here pi is the bar diameter, and now L0. L0 is the sum of the anchorages beyond the center of the support. Normally the value of L0 is taken as 12 into 5. Okay. Normally that value is taken as 12 pi or 10 pi. After that, now here if you move forward, then you will observe that the value of M1 upon V in the above expression may be increased by 30%. Okay, so we have when the ends of the reinforcements are confined by compressive reaction. So now here we have to always we are going to the safer side, even though we have increased each and every value, that is M1 upon V by 1.3%. So from this now, if we come back to our PowerPoint presentation, see here, it is given directly. I have written over here that 1.3 M1 upon V plus L0 from this clause. If you want to go to detail, everything is written there in that clause. You read that clause carefully, you get the idea from where this formula comes. So 1.3 M1 upon V plus L0. And remember one thing, for DCS one subject, there is no any other alternative than reading the IS code. You have to read the IS code continuously, then you try to understand that what is given in that. So M1, generally the value of M1, it is calculated as M1 is equal to MU by 2. So our value of MU, we have already calculated the value of MU. So MU is 15.234 divided by 2, it is 7.617 kilonewton meter. So VU is 19.56. We have already calculated the VU in check for shear. Okay. We have already calculated the value of VU in check for shear. It is 19.56 kilonewton. So if you then also the L0, the value of L0 I have shown here. What is the length? L0 is taken over here. The L0 is the now this is the width of support. This is your slab, and this is your width of support. So you have assumed your support width as a 120 mm initially. So from this point the distance is 120 mm. If I take the center line, or if I take the center, then this is 60. This is also 60. Okay. So the bar which is coming from this side, it will come up to this point. Okay, so this point. So whatever may be the length, that length is from the center to this point of the bar is nothing but L0. And whatever may be the distance here remaining, that distance is the clear cover of the slab. So we have assumed that 15 mm clear cover of the slab. You already know that the bar which is coming from the slab, we cannot end the bar at the ends. Okay, we'll leave some cover. So what is the value of this L0? So the value of this L0 will be the width of support, that is 120. Now this total distance is 60. So 60 minus clear cover if you do, then you will get the value of this L0. Simple if you see this diagram carefully. From this 60, if I minus this clear cover, then I will get the value of L0. That is what it is written over here. This is the formula. So the formula for that is The formula for that is L0 is equal to width of support by 2 minus clear cover. Width of support by 2 minus clear cover, one and the same thing I have told you here. The concept, you draw this diagram. This is very important diagram. I am hoping that simultaneously you are writing it down, all the steps. So L0 is equal to width of support, that is 120 divided by 2 minus clear cover. Clear cover is 50, which is equal to 45. So now if we put all these value M1, BU, then L0 in this formula, so we will get it is equal to what? 551.24 mm. So 554.24 mm. So LD is less than this quantity. LD is less than this quantity. So hence our design is safe from the what we can say development length criteria. Okay, so the check for development length is satisfied also. If your LD is greater than this term, then you need to revise the depth. So you need to go for the revision, you have to change the width of the support, all the things you need to do. So now we will come to the last part of this. Now here, the reinforcement detail. So the simple thing is there, the reinforcement details. I have shown you the section of the slab from the shorter side. So if you see your main steel, if you are seeing from the x direction, that is from the direction of shorter span, then you will see the horizontal bar which are moving is your main steel, and the distribution steel which are along the longer direction and which are perpendicular to the shorter direction. For the distribution steel, you will not see the length of the bar, you will see the dots. Okay, so the diameter of the bar, that is cross section. So if you see, this is the bar which is the of main steel, 10 mm diameter, about 165 mm center. So this is the main bar. It starts from this point. So if I show you here, this starts from this point. This is the bar profile. Observe it carefully. This starts from this point. It comes over here, then it bends, and this will move in a straight line like this. Okay, this is bend, and then it will move in straight line like this. Similarly, the bar, again a second bar, that is alternate bent bars, which starts from this point. It will move certain distance, then bend, and then this bar will also move up to this. Okay, so this is your main steel, 10 mm, about 165 mm center to center. The distances I have given over here. What is the length from the center of the support? If you see, this is the center of the support. From center of the support at a distance of L by 10, this point will be there. At a distance of L by 10, this point is there. So it works out to be 312, which I have shown over here. This is the overall depth of the slab from 135. This is the effective depth of the slab from top up to the center of the reinforcement. Below that, the clear cover is there. And the distribution steel, we have provided the distribution steel of 8 mm bar diameter, and we have got the spacing as a 250 mm center to center. Okay, so this is the distribution steel, 8 mm bar about 250 mm center to center. This is your main steel, 10 mm bar about 165 mm center to center, and this reinforcement detail. This completes your design of one base slab. These are the steps. By using these steps, you have to design the one base slab. Okay, so have you written all the things? Yes or no? No problem. One way continuous slab. Now, as you see here, this is called as continuous slab. 1, 2, 3, 4, 5. This is the continuous panels are there. So you can design this slab as considering one by one panel also. I will consider this panel, I will design for this, then separately this panel I will do the design for this, then all the panels like that. But what will happen in such a type of design, your design will become uneconomical. Okay. theoretically, if you design a separately each and every panel and you provide the steel to each and every panel, these are called as panel. Each this square or rectangle are called as a panel. So theoretically, if you design each panel separately and you provide the steel to the each panel, then it is right. Okay, but practically, if you see that, if you design the each panel separately when it is like a continuous panel, then it is uneconomical for you if you design it individually. Instead of that, in such a cases, we go for the continuous slab. Okay, so the slab which is continuous over two or more than two supports, that slab is nothing called as a continuous slab. So we will see the problem or statement over here. Design a continuous slab supported on four beams and the end walls. The live load on the slab is 3000 Newton per meter square. Use M20 and Fe415. So what they have said, four beams and end walls. So this is nothing but end wall. At end, whatever is shown here, at end, so this is your end wall. This is also end wall, and all these are the beams in between 1, 2, 3, and 4. These four are the beams, and these two are the end walls. And they have given that this width is 7.5 meter, and the center to center distance between each panel is 3 meter. In the exam, this distance may be same, may not be same. Okay. But generally, this distance is same. That is why we have designed it as a continuous slab. So now, considering the one end is simply supported and other end is continuous, the span to the depth basic ratio is 20 plus 26 by 2, which is equal to 23. Are you getting my point? I think most of you are not getting this, how this condition comes. I will tell you. Now, if I consider this panel, just imagine this panel. At this end, the slab is not continuous. Okay, so I can assume that the slab is here. The wall is there. The slab is resting on this wall. So, and there is no continuity of the slab to the left hand side. So I can say that the slab is simply supported at the left hand. But if you see the right end, at this end, it is not simply supported, it is continued. Okay, the slab is continued over the right hand support. So here, what we have said that one end is simply supported. So this end, it is simply supported. And the other end is continuous. So here, the slab is continued till on the further support. Okay, so other end is continuous. So basic span to depth ratio is taken as 20 plus 26 by 2. So from where this comes, so 20 for simply support, simple support, 26 for continuous support. But here in our case, we have taken one support as a simple support and other is continuous. So we are in between that. So we have done that. We have taken the average of these two. 20 plus 26 divided by 2. Now if I share the IS code with you, you will get this span to depth ratio. We have already seen that the span to depth ratio. Okay. So where is that span to depth ratio? Which clause? Do you remember? On page number, while selecting the depth of the slab, I think the page number 36 or somewhere, no, or 37 here. Simply supported. See, for simply supported, the value is 20, and for continuous, the value is 26. For simply supported, it is 20, and for continuous, it is 26. Now, in our case, our left end is simply supported. If you consider the panel, our left end is simply supported, but right end it is continuous. Okay, the slab is continuous. So we are coming under both these conditions. So what we have done, we have taken the average of these two. So 20 plus 26 divided by 2, it is 23. So that is why in our slide here, we have got the value as a 20. Okay. So after this now, as usual, we assume the percentage of steel, and here the percentage of steel is 0.3%. We have assumed the percentage of steel as a 0.3%. Again, from figure number 4, page number 38, we have to calculate the modification factor, and from that we are going to calculate the effective depth. So d depth is equal to, what is the formula? So here we are designing the end panel of all these continuous panel. So if we consider this end panel now, so d is equal to, what we can say, span divided by 20 into modification factor. Okay, 20 into modification factor. If in the now here the question in the exam for you to design the continuous slab, but you have to design one panel. Either you can take end panel or you can take central panel. But in the problem, if they have mentioned you to design the end panel of the continuous slab, then you have to design these two panels if end panel is there. Okay, and if in the problem it is mentioned that design the intermediate panel of the continuous slab, then you have to take this panel for the design. Okay, and if they have asked you to design the intermediate panel, then if you see this panel, the left end is also continuous, right end is also continuous. So for the continuous slab, we should take the ratio as span to depth ratio 26. So instead of 23, here if you are going to design this intermediate panel, you should consider here instead of 23, 26. Now, but in our case, in the problem, nothing is mentioned that design end panel, design intermediate panel. So we will consider this end panel and we will consider this condition. So now here the span is equal to, depth is equal to span divided by 20 into modification factor. This modification factor is 1.4. It is calculated from this page number 38, figure number 4. I hope you are clear with this now, how to look this figure number 4. So again, you see that our percentage of steel assume is 0.3. So now from this, you get the value of D as 93.60. So assuming 15 mm clear cover, 1.5 and 10 mm bar diameter, you can calculate the overall depth. Overall depth D is equal to, what is the overall depth? So effective depth plus clear cover plus half of bar diameter. So the overall depth is 113.16. So we round up this value. So if we round up this depth, then it comes out to be 115 mm. Okay, this is our overall depth. So from this overall depth, you can calculate the effective depth. So effective depth is equal to 115 minus clear cover minus half of bar diameter. So if you do this, you will get the effective depth. So this effective depth, it is 95 mm. This is your effective depth, which is 95 mm. Now after this, we are going for the load calculation. So for the load calculations, same thing which we had done in the design of one-way slab. The only minute change here is you have to calculate your dead load separately and your live load separately. Because while calculating the bending moment, the different coefficients are assigned for dead load as well as for live load. Okay. So here, if I show you the dead load, so dead load that is self weight of the slab. So the self weight of the slab is nothing but the thickness into density. So the thickness means depth. So our overall depth is 0.115 into 25. Whatever value, that value we will get in kilonewton per meter square. So still it is not a load. It is not neither a UDL nor a point load because its unit is kilonewton per meter square. So you can say that we got only the intensity of the load. So it is now in kilonewton per meter square. So after that, the floor finish 1 kilonewton per meter square assumed value, as we have seen earlier also. After that, total dead load. So these two values comes under the dead load of slab, that is self weight and floor finish. sulfate of slab and chlorphenol. These two comes under dead load, and if we add these two quantities, then it is 3.875 kilonewton per meter square. Now factor dead load. Factor dead load means we multiply this value by 1.5. So multiply this by 1.5, we got this value 5.81 kilonewton per meter square. Now lie load. Lie load is given in the problem itself. It says that 3 kilonewton per meter square. Or that we can say 3 kilonewton per meter square means 3000 Newton per meter square is given. So convert that Newton into the kilonewton, it will be 3 kilonewton per meter square. So sometimes in the numerical also the load is not given. Live load, they may not give you the live load. Okay, they may not give you the live load. So you remember this in the case of residential building. In the case of residential building, your live load on the slab varies between 2 kilonewton per meter square to 3 kilonewton per meter square. In the case of residential building, write it down, it is very important. And in the case of public building, it is fast होता है क्या? Okay, I got one suggestion. I am taking very fast, so I have to slow down my speed. Okay, I will slow down. So I was explaining you about the live load. So you remember this, you write down in the margin somewhere for residential building, if in the numerical itself the live load is not given, and instead of that they tell you that design a slab for residential building, design a slab for commercial building, or design a slab for public building. Sometimes they may use this type of wording. So whenever the residential building is there, then in the residential building, your what we can say live load is varies between 2 kilonewton per meter square to 3 kilonewton per meter square. Okay. And for the public building or commercial building, it varies from 3 kilonewton per meter square to 5 kilonewton per meter square. So for public, you generally take it as a 5, and for residential, you take it as a 3. Okay, if the values are not given in the problem. So fine. So now again, live load 3 kilonewton per meter square. So multiply this live load by 1.5, that is factored live load. It is 1.5 into 3, so it will be 4.5 kilonewton per meter square. So now assuming the 1 meter wide strip of slab. Okay, if you assume the 1 meter wide strip of slab, then if you multiply this value by 1 meter, this value is also by 1 meter, because we are assuming the width of slab as 1 meter. Okay, so if we assume the width of slab, actually the width of slab is 7.5 meter, but we are not taking it as a 7.5 meter. What we are doing, we are assuming the width it is 1 meter. So if you multiply these two values by 1 meter, then we will get UDL, that is dead load UDL as UDL of dead load 5.81 kilonewton per meter, UDL live load, that is WUL 4.5 kilonewton per meter. Okay, so this is the loading, and the bending moment calculation, and the next we will see in the next lecture. Till now you revise the things which we have covered today.